Mic check, audio check. 1, 2, audio check. 1, 2, audio check. Okay, hello, and welcome again to another episode of us just trying to discuss some physics. So today, I actually had a quick discussion with a student today, and one thing that we were trying to tackle is why do we use the Dirac Delta function uh, when describing some densities in some scenarios? And so I'm gonna go over that briefly. Um, it has a lot to do with the way we kind of look at space when we're trying to integrate. So normally, in say Griffiths, when you're learning an intro to E&M, say for like an advanced physics course, or a little bit past your normal intermediate that you might take your freshman or sophomore year in college, um, you might be giving several point charges, right? This might have Q1. You might have another point charge right here. Maybe it's minus Q2. Or we could just give integer values to this. And you might have a collection of them up to, say, Qn, where each of these just have their own value. And normally, the way you're kind of given this is just you have a collection of charges. And the total charge of the system just happens to be equal to the summation of all these charges. And they'll write it such as this, where you're basically just looking at the sum of the charges, right? And so if they gave you an initial board, say a space to work with, and they said, well, sum up all the charges. You just look at the point charges, get the value, and we're good. Um, and so, but if someone was to tell you what's the density of this, how do you really explain a density when you're given point charges? If you're given a space here, and say we have a circle, and you know it has uniform charge density. Well, someone could just tell you that, okay, the density of this, say, as a function of r, and say this is a center point, and this extends out to a radius r, and the density is rho naught. Someone could give this to you, this equation, and just say, okay, well, uh, your densities are not, or rho naught, when your r value is less than r, and it's 0 otherwise, right? And so that's one way you could describe it. If you just were looking at a whole entire block, you could come up with a similar thing. Or say if you're now looking at a new space and you have this, you center, let's say the origin is right here. This is XY coordinates. So someone could then tell you, okay, say this is distance L and L. They could do the same thing here. If you have rho naught, if X and Y are less than or greater than 0, but less than L. And so now we kind of have a basis for understanding at least just this density. And so when you integrate, you want to find out all of your Q, you could just integrate all space, right? So this notation denotes I'm integrating over the whole entire space, and this is the value that I'm going to get. And this integral in this case, so to remember, you're always integrating the full entire space. So whether you're Cartesian coordinates, spherical coordinates, cylindrical coordinates, or whatever coordinate system you want to deal with, you're always integrating all space. It's just a lot of it will be 0, right? So let's just even take this for example. In this case, it would actually only be a double integral, right? Or whatever. We could expand this to 3 dimensions, right? And so you'd have a cube. And so this could be z component, and so we have this whole entire cube filled. So now we could go back to our three-dimensional integral. This still holds, but a convention would tell us, well, hold up, we technically only have um, a density within this region, so shouldn't we only integrate over there? Well, yeah. Well, the thing is, this would end up being equivalent to just reducing your integral to this. Why? And that's because the rest of the region is 0. So even though you're integrating in the other regions, those values are equal to 0. Right? Because this is equivalent to integrating all the other spaces that basically aren't. So it would be like negative to infinity to 0. And then I'd actually have to write a whole entire series of these different integrals, but you get the point. The other integrals basically end up just being 0. So the complement of this volume is 0. So you don't need to, because remember, integrals could be broken up. This integral is equal to this. So if we're just looking at the one-dimensional equivalent, these would be 0. This would have rho, right? This would be the generalized function. Okay, and so kind of going back to this point problem, well, what if we had a blend of these densities with points? How do we then look at these points? Well, if I still wanted a way to write this density out, right? I need a way to describe me integrating over an area such that it encompasses points. So the equivalent of this is just doing the summation of these points, right? But we might not have the privilege of that. So one way to get around it is the usage of Dirac Delta functions, where this could still be a sum, but we now have a delta function to tell us whether we actually have a point there or not. So let's just take the simple case. We just have Q, and our Dirac delta is literally at the center point, right here. It's just we have a point charge there, and so when we want to find the total say charge in here enclosed in our surface in our container, let's say that we want to integrate over any type of region, right? So this is going to be an actual volume. What we end up getting here, we'll see, is this integral over a volume, and this is a specific volume, V. It might contain this point, it might not. So when we plug in this here, I can make this a different color. We get constant Q out over the Dirac delta function. Since Q is constant, we can pull it out. And then now we have this, the integral of this Dirac delta function. And so I think I might have to make a whole separate video on this. But what you have to recognize is this is equal to either 1 or 0. And this is dependent on um, whether x So this is going to be dependent whether the point source right here, which is at 0. So I'll write the vector in the in the notation of the 3 vector, whether this is contained in the set of the volume. What this means is the space that I'm integrating, does this origin point, is this contained in the volume that we're integrating? Because remember, this could be all space. If this is all space, then yes, this integral is 1. And what will our value be? It'll be q if it's enclosed, right? But let's say, we'll just look at the two-dimensional representation. Let's say that if I integrate over here, then yep, this integral is 1. If I was to integrate here, it's 0. If I'm to integrate everything and then leave out this, it's 0, because this point charge is not enclosed in this volume, right? And we'll do another example. If I was to integrate everything, seeming like I'm about to leave it out or encompass it, leave it out, then I could just do whatever I want. This volume still does not enclose this, so this would be 0. An example of, we'll do one more. So if I was to do a massive integral over here, and then I do encompass it right here, this encompasses it, so this would actually be equal to 1 based on this integral that we're trying to solve right here. So that's how this Dirac Delta function works. Is this encompassing it? Yes or no? I think I might go over the mathematics more of it later on. Because just to make this clear, because this might actually just leave a lot of unanswered questions. The answer to this is probably written better as x minus x naught. So we're saying the vector x naught is the point of wherever we're at. So if say we had a point charge here and this is x naught, a vector, this is going to be equal to the same thing here actually. This is going to be equal to 1 if our vector x naught is in the volume and it's 0 otherwise. We'll get to play around with this more later on, but I just wanted to kind of quickly show why this Dirac Delta function might be important or utilized in otherwise kind of seemingly random way. We'll use this more as we kind of go a little bit more in depth into our electrodynamics journey. But I hope this is helpful. And if you have any questions regarding this, please leave a comment or in the chat. And I hope to get to it in the future. All right, y'all have a good night. Bye bye.